should we use? Or 8th grade science? Science time, Brown. We are going to talk about today mechanical waves. Mechanical waves. Oops, let's get that nasty stuff out of there. Yeah, I would like to do a little demonstration for this one too. I think that's kind of fun. It's fun for me, and I hope it's fun for you. But in a much more real sense, I don't really care what you think. Why don't you go get me that same aluminum pan that you used for your lab, those little baby ones. Sage, I'm talking to you, and fill it up about a third to half of the way with water, please and thank you. What's a wave? You should already know what a wave is. We talked about waves last time. In the last video, we talked about waves. Is waves only about water? No, and to demonstrate that, I'm going to use some water and make some waves in it. No, waves are not just about water, but waves, remember, is any kind of repeating or oscillating occurrence of energy transferring from one place to another. That's a wave. We had two different kinds of waves we talked about. We talked about longitudinal and transverse waves, and now we're talking about mechanical waves, which are not a whole separate type. They are just waves that take waves where energy, well, let's try to spell energy correctly to begin with. Energy is transferred through, fill in my blank. What does a mechanical wave have to be in? Mediums. Yes, a medium. Through a medium which is made of matter. Through matter. And we call this matter, whatever type of matter it is, just put on the table there. Whatever type of matter this is, we call it a medium. Remember, we talked about how the plural of medium is, was this you I talked about this with? No, it isn't. This is with earth science. The plural of medium, does anyone know? Ramrock, if you do. No. Ramrock, if you do know. The singular is medium. One, medium. Media. Two or more. Media. You don't get a Ramrock because you had several guesses, but the plural is media. Does this mean something to you? What's social media? What are social media? TikTok is a kind of social medium. Snapchat is a kind of social medium. What does that mean? It's the way that we socialize. It's a thing through which we can socialize. My talking to you as a human being talking to another human being is a social medium. We don't list that as part of the social media when we're talking about it. When our grandparents are trying to scare us into never using TikTok again, we don't list talking to other people as a social medium, but it is. A social medium is just a way through which we can socialize. So a medium is a thing through which another thing flows, for instance. What's the physical, what's the material, what's the matter, medium, through which I'm speaking to you right now? Air. Yeah. Yeah, so just in the exact same way that TikTok is a way through which you can get information, social information from other people, air is a way in which we can get sound information, wave information, from one place to another. So media is the plural of medium. If I'm talking about multiple media, one medium. But it has to be made of matter for it to be a mechanical wave. What's an example of a mechanical wave? Water wave. Water wave. But the one we're going to talk mostly about is sound wave. What is the medium of a water wave? Water. Water. What's the medium of a sound wave?
Air.
Not always. Can sound travel through solids? Yeah. You're too broken, so you can't. Tommy, put your ear on the table right now. And then, Tegan, would you knock on the table? Do you hear it in your special ear, Tommy, the one that's on the table? Yeah, you do. In fact, it sounds weird, though, kind of, probably. Something that's really interesting. Have you ever been swimming? Raise your hand if you've swum. If you have done swum. You have swum. Fia, you never swum in your entire life. Okay, raise your hand if you've been swimming in a body of water in which there were also motorboats while you were swimming there. Have you been underwater and a motorboat is somewhere and the whole water just sounds like in your ears? Has that happened to you? Can you tell from which way the boat is when you're underwater? No. Your ears are designed to hear sounds in air because you live most of your life in air. And so The way, and you don't think about this happening, obviously, but the way it works is if Garrett is whispering to Sage, which he shouldn't be, but I hear him do that, I know he's to my left, because without even realizing it, the sound has reached my left ear before my right one. And so I know that sound came from the left, and so I can turn that way. And we're designed that way so that if there's a rustle in the bushes over here, what is that? It's a tiger, and the tiger eats you. And you can run away from that if you know from which way the sound is coming. But you don't spend a lot of your life in the water. And so for you, the difference between left ear and right ear in the air is noticeable. But the difference between left ear and right ear in the water is not. It just sounds like it's coming from everywhere. Because you are not built to understand the direction from which sounds are coming in water, whereas fish presumably are. What does that tell you about how sound is different in water and air? Okay, in a given area there are more molecules in water, and so the sound can travel faster. Yeah. There is a speed of sound. Sound has a speed, speed at which waves propagate through that material. And in decreasing order, what do you think the fastest speed of sound is in?
Air.
No. Try again. Light is not a material. The speed of light is faster than all of them. I think that's what you're getting at, but the light is not a medium through which sound can travel. Well, what's the slowest, maybe?
Water.
Let's put no speed at the bottom. Where can sound not travel because there's not matter?
Space.
Vacuum of space. Yep, the vacuum of space. Where would it travel slowly? So we go down here, we have no particles. Lucas said that somewhere here we should have water, which has more particles per volume than air. Where should I put air then?
Up.
This is a pretty simple logic problem. Yeah, it's slower. It's slower. We're going from no particles, spread out particles, less spread out particles. What would be faster than that still? A solid. Let's put table at the top. I mean, there's probably things. The more tightly packed, the point is, the more tightly packed the molecules, it doesn't have to be molecules, the more tightly packed the particles are, the faster the sound can travel through them. Because the sound propagates as, remember, if we think about the wave like this, what's really happening, or let's not think about the wave like that. Let's think about it as a longitudinal wave, which it really is. The particles close together in a, what is the vocab word for close together part of a longitudinal wave? Remember? Compression, yeah. They're close together in a compression and far apart in a, what's the vocab word for this? Rarefaction. Rarefaction. And the more particles there are, the more it can be compressed. Or the faster it can happen. The quicker the sound can move from one particle to the next. So what has to happen for this wave? Remember, the wave itself isn't moving. What has to happen for the wave, the energy of the wave, to move from here to here? What has to happen? These particles have to do what? No, the particles don't move. The particles have to vibrate, but they have to bump into the one next to them. This whole thing is like dominoes. The whole thing is like dominoes. And the closer together they are, the faster the wave can propagate. Because what has to happen for the energy to get from one place to another is that the first thing has to bump the next thing, has to bump the next thing, has to bump the next thing. And the faster that can happen, the faster the speed of sound is. It's all about bumping. What's bumping here? Dominoes. What's bumping here? Atoms. What's bumping out here? As my sound, remember, we talked about this last time, but when I talk, my vocal cords, the air that is inside of here is not going out to you and getting inside your ears. And it's not like each little air molecule is an envelope with a little message that says, message, and the little atom goes into your ear and tells it to you. That's not how it works. What happens is the air here vibrates, and that causes this air to vibrate, and that causes this air to vibrate, and really pretty quickly, the air all the way from me to you, each individual air molecule has vibrated and bumped into its neighbor, which causes him to vibrate, etc., etc., etc. And that happens so fast we don't even realize it. That is what is happening. Each little atom, remind yourself, how does this one specific little atom right here move? Does he go all the way from here to here? No. Bad. That's wrong and stupid. What he does is he just goes back and forth. That's it. One little air molecule, and that bumps into the next one, bumps into the next one. The closer they are together, the faster that bumping can lead to where the energy's destination is. Table has closer together particles, so it's faster than that. In a vacuum, there are no particles, and so no mechanical wave can propagate. Look at the chart on page 27. You don't have a page. Look at the chart at the end of page exploration 1 called sound speeds in various media. There are a whole bunch of different media here, and it has the speed of sound in meters per second for each. What is, on this chart, what is the slowest speed of sound? It's on page 27 in the physical books. No, that doesn't count. The answer is no solution. It's not even 0. There just is none, so we don't count that one. What's the slowest speed of sound on this chart? 27, Miranda.
Yeah.
Yeah, what is it? Answer me then.
Gas.
No, which specific gas?
Oh, argon.
Argon is the slowest. As a side note, why is it important for you to read charts like this? Yeah, that's true. The chart is a nice, concise way to show information. Tommy, say yours. This is a
So we do good in our tests?
yeah. This is a really like a short-term benefit, but it is so that you do good not only on your tests in this class, but on the maths test and the ACT. It's all about reading charts. There's a pretty direct correlation with someone's IQ and how well they can read charts, and that's not immutable. It's not like you're born. Well, you know what? Babies are stupid. I'm going to be straight up with you. Babies are dumb little critters. My son's getting smarter, but babies are stupid. IQ 0. They can't do anything. As they grow up, their IQ gets better and better, and yours can still get better. Your IQ is not stuck. You might think of yourself, because this is kind of getting into motivational talk territory instead of science, but you might think of yourself as someone who, I always get a 199 on my MAPS test, so I'm never going to do any better. But I have seen with my own 2 eyes people make 30-point leaps in a single year on MAPS test. Doesn't always happen, but it can happen. It's not immutable. If you are not good at reading charts right now, get good, dog, because you will get much better. Your whole life will be a lot easier if you can read a chart. So, argon has the slowest speed of sound. What has the fastest speed of sound on this list? Aluminum. Aluminum has the fastest speed of sound. What do you notice about the state of matter? We're not looking at specific media now. We're looking at which state of matter. Do you notice a pattern in the states of matter on this chart?
Yeah, it goes gas, liquid, solid.
It goes gas, liquid, solid. How is this chart organized? Is it alphabetical by medium? No. Is it in order gas, liquid, solid? No. It goes from fastest, it doesn't. It goes from slowest speed of sound descending to fastest. But the pattern still shows up in the state. It's not organized by state of matter, but the pattern shows up. All 3 gases are slower than all 3 liquids, which are slower than all 3 solids. Do you see that? Because the particles are closer together by definition. This is what defines solid, liquid, and gas, as we talk about next year in physical science. In fact, the day before yesterday, we talked about this in physical science. That was Sunday. That didn't happen. Friday, we talked about this in physical science this year. But the definition of those things is that in a solid, the particles are tightly packed. And in a gas, they're very spread apart. And that determines the speed of sound, exactly as much as it determines what state of matter it is. Let's look at this little guy. Oh, this is not going to go very good, I don't think. If I turn this down, okay. Let's get the keyboard off of here at least. Is there water there? Okay, I'm going to get my little marble. I don't even know, I don't have the video editing skills to do a good job of this, but I wish I could slow this down because I think this will be kind of neat. Can you come gather around, but don't get in the camera? By the way, if you do get in the camera, you did sign a video and photography release waiver, but I would prefer if you did not. So come get in here. Don't get in the camera. Gather around, Fia. Can you see it from here? Cody, you little devil. Get over here so you can see what's happening. I want you to be able to see the top of this water. So here we have, what could we call this? A marble. And what's it going to do to the medium here? It's going to, yeah, if we're being scientific, we might say that it's going to disrupt the medium. What kind of medium is this?
Water.
A liquid, right? Ah! Did you see it?
Yeah.
I'm going to fish it out. I wish I had a bigger one. Would you go get a bigger one, please? Right now. I don't know. Just find
Get someone's eye.
Pay attention, let me see, wait till it's still again, but pay attention to something over on the side and see how you can, if you can tell, I wish it was slow motion, but see if you can tell I'm going to start it over here, pay attention to something on this side, see if you can tell how the wave is propagating. I missed, sorry. Do you see that? What happens to the water over here? What's the water over here? Just the water over here, what's it doing? Yeah, up and down. Which way is the energy moving? From the disruption out in 3 dimensions, right? How can you tell it's in 3 dimensions?
Because water goes up.
Yeah, you can see the water splash up. You can infer that the water is also moving down. The water itself is not. The wave is moving down through the water, and we can see the water, the wave, move from one end to the other. But each little individual particle of the water is just oscillating. It's just going, and it's not going. Whoosh. I wish now I don't even want Sage to get that thing anymore. I just wish I had something that can float. I have some pencil shavings here. This is something that can float. You know how when just knock it off, Sage. It's okay.
It's not marbles,
Knock it
but
off, Sage.
What?
You said knock it off.
Oh, you misunderstood. I wanted a bigger pan, but that's okay because I don't actually want any of them.
Misunderstood, Sage.
shake it up.
Okay, little guy, you better knock it off. Get over here. You sit still, you little devil. Why does it have any motion at all? Why does it have any net motion?
Because you pushed it.
Yeah, because it's still, the water is relatively low friction, so if I even put a tiny force on it, it's going to move, maybe not forever, but for a while in a straight line at a constant speed. But it's more or less still there. Let's see what it do when I do this. Tommy. What I hope you saw, it is kind of moving now. There's a current in the dish, but I hope what you saw is that the pencil shaving did not, as you probably thought if you were a dumb little baby, what you probably thought was going to happen was the wave would carry it from here where the disturbance was over to the edge, is what you would have thought if you were a dumb baby, but that isn't what happened. It did move, but it actually moved the other direction. Let's try again. Look at that. See, it doesn't even, if the wave were movement, if the water were moving from the disturbance away, if the water, all of that water moving, the leaf would have moved with it, wouldn't it have? But it didn't. It just stayed in one little spot. In fact, you could even see it go back and forth. You didn't really see it go up and down, maybe, but that's a wave. That's a mechanical wave. Go sit down right now. Oh, that's really not going to work very good.
What are you doing?
Okay. So what happens when the wave, I'm going to erase this little definition thing up here. What happens when the wave gets to the edge? I'm going to draw it from the top like we saw it in the video. What happens when the wave, which started here, gets to the edge, which this is not this shape, it should be flat. That's flat. What does it do? Bounces back. There are 3 things it can do. When a wave, I'm not even going to say a mechanical wave because this is true of all waves. When a wave interacts with matter, 3 main things can happen. Bounces back. What do we call that? You know from your exploration, I hope. What's the fancy word for bounces back? Reflection, yeah. Ricochet. That's especially fancy because it sounds French. Ricochet. Okay, reflection can happen. What else? What else can it kind of do, and did it do? So first of all, it reflected. After it hit this, it went back the other direction. The wave did. The water did? No, the wave did. The energy did. Okay, so it can reflect. What else can it do? Well, we get a hint in, is it still, if it only did this, what would it still be doing? It'd still be going back and forth all the time. The water would still be reflecting. So what else can it do? Yes.
Slow down.
Yes, there's a fancier word, and it's not just doing that. The little pan.
Friction.
Friction, because of friction. No? What?
Go through it.
Yes, that's not what we're talking about here, but we're going to go through it down here. What else can it do? Be
Awesome.
Be awesome.
Stalemate. Absorption.
Absorption. I try to do hangman, I kind of got these ones. Absorption. It can be absorbed. The wave can be absorbed by the medium. Which means, in this case, that the energy the energy that was carried by the particles of water that were oscillating is now oscillating in the pan. Hey, did you hear something when I did this? So it's not just a wave in the water. The wave starts out in the water, but the water particles bump even an air particle, or they bump the pan particle, and the pan particle bumps an air particle, and that's sound. That's what we hear as sound. So when you hear the marble drop, it's because the molecules, the particles that are next to where the wave formed, where the disturbance happened, bump the next particle, and that crosses over medium. It starts out in the pan, bumps the particles of water, which bump the particles of air, and that bumps the particles of your eardrum, which make your eardrum vibrate, which make you think, oh, I heard the marble drop. That's absorption. And it can also go through it, which is called transmission. Transmission is to go through. It goes through. So if we're thinking about a little particle here, or this part of the medium transmits the wave to the next part of the medium. What's another kind of wave that we think about very frequently? We have sound waves that we think about a lot. We think about water waves. Some of us think about that a lot. But what? Say it again, Cody. Say it again, Cody. Oh, no. Yeah, microwaves is a specific type of light waves. Let's start a whole new thing because light waves are not mechanical. Light waves are not mechanical. But light waves, they exist still. They don't have to go through a medium. So let's think about each of these three things in the terms of light waves. How can light reflect?
Mirror.
Only a mirror?
No.
No. Look at this. Shirt. Thanks. Great example. Shirt. I thought it was you, but it was actually you. Yeah, shirt is the way. But the classic example that we use is that your shirt. Let's use not shirt because that's too classic. Look at the lid of Tegan's Gatorade bottle. Is that lid emitting its own light? No, maybe, but not very much. It's not emitting visible light. What's happening is the light from the sun is transmitting through outer space, which light waves can travel in a vacuum. Can travel in a vacuum because they're not what? Yeah, they're not mechanical waves, but they can travel in a vacuum. So the light waves are traveling through outer space, transmitting through the atmosphere, transmitting through this window, hitting the lid of Tegan's water bottle, and reflecting back into the room. And that's going into your eyeballs, and your eyeballs are thinking, oh, orange, because they see that specific wavelength of light. You know what I mean? All of these can be, so reflection, the orange of my marker is reflecting orange light. Absorption, what colors of light is this mark absorbing? Well, if it's reflecting orange, what colors is it absorbing? All the other ones, red, yellow, green, blue, purple, indigo. How does what can transmit light?
Windows.
Yeah, only windows? No. What do we call the kind of material that can transmit light well? Transparent. If it can transmit light well, but not an image, we call it translucent. And if it doesn't transmit light at all, we call it? No. Opaque. We call it opaque. If it can transmit an image, we call it transparent. I think this is in the next chapter, but we're going to talk about it now anyway, because why not? If it can transmit only the light but no image, we call it translucent. And if it does not transmit any light, we call it opaque. These apply to all waves. This stuff, actually it does apply to all waves too. The speed of light is different depending on how tightly packed the particles are too. One reason that diamonds is so beautiful, you ever see a diamond? One of the reasons diamonds is so beautiful is because the speed of light is very slow in a diamond, just like it's very fast in air. It's inversely proportional in light waves. And since it slows down so much, it spreads out for one thing. It makes a beautiful rainbow of colors, but it also bounces at a different rate, so it gets what we call the fire of a diamond, and it can reflect light in really pretty ways. Do you have questions about the interactions of specifically mechanical waves, but also more broadly the interactions of any kind of wave?
Yeah, what are those words at the bottom?
None.
No.
Opaque.
No.
I'm not going to answer your question. I'm not going to go through every single word I've written. What word do you have a question?
On the bottom.
Can travel in a vacuum.
Bottom.
Image.
Oh.
Bye! Get out of here, Lucas. Bye! I'm just kidding, Lucas. You're a good boy. Bye.